Last goal for this first day of Chapter 2, finding values where a function is or is not differentiable. So, not differentiable. What our assumption, first off, should be a function is going to be differentiable most places, meaning able to find the value of the derivative at specific places. Your assumption should be that it pretty much is until you find exceptions. That's kind of the way things are going to go. So I'm going to jump to this backside. So we did definition, we did alternative form, we found out the function 3x squared plus 2 actually was differentiable, particularly at x equals 1, because we were able to find that its slope of its tangent line at x equals 1 came out to be 6. Well, how will we know if a function's not differentiable? Find the slope of the tangent line to f of x equals absolute value of x minus 2. Absolute value of x minus 2. How do you find the derivative of an absolute value? Well, we could do definition of the derivative. We could do alternative form. You're not going to like either result. It's going to be ugly. But here's what we do know about this thing. F of x equals absolute value of x minus 2. Absolute value of x minus 2 would be a V graph. The point of that V would happen at x equals 2. There would be how my graph would look. It would look something like that. On either side, the slope would be, on the right, the slope would be 1. On the left, the slope would be negative 1, because it would be basically two linear functions coming together at x equals 2. Well, what do we have here? Well, according to this is a sharp turn in the graph. Why is it a sharp turn in the graph? Well, think back to the days of if we were to define what this really looks like. F of x, if we were to write it as a piecewise function, well, to the right of x equals 2, in other words, when x is greater than or equal to 2, we would have the function x minus 2. Well, to the left of x is 2, that would be, well, wait a minute, it would have been the same x minus 2 function, but because that part of the graph was below the x-axis, the absolute value would have effectively flipped it above the x-axis. So that is the opposite of the quantity x minus 2. Well, if I wanted to then do, I could do definition of the derivative on either side. Long story short, what I have is, I have this two completely different functions, and they're going to just abruptly change at x equals 2. And when things abruptly change like that, that's when we end up with this thing that we're going to call a sharp turn. So functions are not differentiable. So this is what we're going to look for, differentiability. Okay, functions are not differentiable at, first off, discontinuities. So that means holes, that means asymptotes, that means jumps, that means, what am I missing? I guess those would be the big ones. Any kind of break in the line, function's not differentiable at that specific x value. Part B, functions are not differentiable at sharp turns. And C, vertical tangents. So if somebody is asking you to find places where a function's not differentiable, you're going to look for these things in this particular order. The most common thing that you'll find is a discontinuity, and we've already talked multiple times about how to find discontinuities. Second most common thing is going to be these sharp turns, much as like this one. And last is vertical tangents. Vertical tangents you're not going to see very well. So let's take an example right here. So this next question, find any values where fx equals 1 over x minus 3 quantity is not differentiable. Well, I can tell you as I look right there that this function is going to be discontinuous at x equals 3. Well, if it's discontinuous at x equals 3, then this thing is not differentiable at x equals 3. Now, just for a little check for yourself, is that a hole or an asymptote? Well, we can't factor and cancel the x minus 3 away, so that's going to be a vertical asymptote. But either way, this thing is discontinuous at x equals 3, therefore it's not differentiable at x equals 3. So if somebody says, you know, give any values where this thing's not differentiable, it's differentiable at every other place. We could find a value of the derivative at every other place except x equals 3. So that's kind of the way we're going to look at it. Now, in this little theorem that we've got going over here, if a function is differentiable at x equals 3, it's x equals c. If it's differentiable at an x value, then that means it's got to be continuous. So if you are given, for whatever reason, the value of the derivative at x equals 12 is this number, well, that must mean that the function is also continuous at that number, if that makes sense. So according to this theorem, kind of file this one away, because this will be something that as we start studying AP stuff, these are some of the more detailed type things that we're going to need to come back and review. So if a function is differentiable at a number, then it's also continuous at that number. And there's some of your practice stuff. So there's ways to figure out if a function is or is not differentiable at an x value.